Hey everyone, welcome to this video on the CT physics. This video is meant to be a short review. So first we're going to talk about the production of X-rays. There's an image there of an X-ray tube. X-rays are produced by colliding electrons from a filament onto the target. The filament is the filament gets really, really hot and it essentially just boils off electrons and shoots them towards the anode. So the uh, higher voltage will accelerate the electrons to a higher energy. The electrons undergo ionization and Bremsstrahlung interactions in the anode. And then Bremsstrahlung and characteristic X-rays are directed outside the tube as part of the X-ray beam. Now, Bremsstrahlung is most common, but it's not what we want. We actually want the characteristic X-rays. And the operator controls the milliampere and the kilovolt potential settings, the MA and the kVp. So this filament circuit is what delivers that high voltage supply to the filament, and then the filament gets really, really hot. There's a lot of heat released in this whole process. But the filament gets really, really hot, boils off those electrons, directs them towards the anode, and then they interact with the material in the anode. So the kVp setting essentially correlates to the energy of the X-rays, and the MA is the amount or the number of X-rays. So this is an example of a couple of commercial X-ray tubes and then a closer up image of the X-ray tube itself. So this envelope is often made of glass. The entire process is in a vacuum, and we want it in a vacuum because that helps to control the action or the interactions and what happens within the tube. So we actually want the characteristic X-rays, and the Bremsstrahlung just happens with it. But we don't want a lot of other things. We don't want scatter. We don't want those electrons to be, we want them to be directed straight at the anode. And so the best way to have that as a controlled environment is to have that in a vacuum. And then this is actually the type of X-ray tube where the anode will rotate. The older ones, it was stationary. The newer ones, it will actually rotate. This helps to dissipate the heat because it is a very hot process. There's a lot of heat generated. And it also helps to, interact the anode, the electrons across the whole face of the anode rather than just one small part of it. Let's take a minute to review the X-ray physics. Now, like I said, the interactions that happen in the X-ray tube are characteristic X-ray and Bremsstrahlung. Both of those come from interactions of electrons with matter. Electrons are a charged particle, so as the charged particle interacts with the atoms that make up the anode, then that interaction will occur and release X-rays in the process. So with characteristic X-ray, the electron will actually interact with an electron within the atom and kind of knock it out of the atom. So an electron is ejected typically from an inner shell, and then the energy is released as an X-ray when an outer shell electron drops into the place to fill the vacancy. Remember the octet rule, and the electrons want to be as close to the nucleus as they can be. They're attracted to that. So the inner electron shells will be filled before the outer shells will. Inner shells should always be filled. So if an electron is ejected from the inner shell, then electrons from the outer shell will automatically drop in to the inner shell to take its place. When that happens, there is a difference of binding energy between the electron shells. So it depends on which shell of electrons are the electron is ejected from and which shell the new one dropped from. But there's a difference in binding energy between those X-ray shells or those electron shells. And so as that exchange happens and the outer shell drops into the inner shell, it releases the X-ray as excess energy. The energy of the X-ray is characteristic to the binding energy between those energy shells where that initial drop down effect occurred. So characteristic X-rays, we say they're characteristic because they will always be a certain energy depending on the energy shells that were involved in that interaction, but they will be different. So a K, an L and M shell will be very different from a K and M shell or whatever. So that's where the difference comes into play, and that's why the X-ray beam that actually comes out of the tube is a range of energies, even though it's set energies characteristic to where that occurred. The other interaction is Bremsstrahlung. Bremsstrahlung really means breaking radiation or slowing down. And with Bremsstrahlung, that electron from the cathode will be attracted to the atom, and it'll be attracted to the nucleus because electrons are negatively charged. Remember, the nucleus is going to be positively charged. So it's attracted to it, but as it actually interacts and is working its way through that electron shells, it slows way down and changes directions. And so as it slows down, it loses some of its energy. The energy actually will get absorbed by the atom, and then the atom releases that excess energy as an X-ray. These are usually low energy X-rays, and they're not really what we want for imaging, but it just occurs because of the electrons interacting with matter. So characteristic X-rays require 70 kVp or higher based upon the energy of the K-shell electron. And Bremsstrahlung X-rays can be produced at any projectile electron energy. In diagnostic radiography, most of the X-rays are Bremsstrahlung X-rays. We want characteristic. We want them to be 70 kVp. Usually what we want for CT is like 70 to 140-ish keV or 120 keV. And that's typically what we want. The Bremsstrahlung tends to be a little bit lower energy than that. So the X-ray tube design, like I said, is an evacuated glass container. We want that to be in a vacuum so that it's a more controlled environment. The cathode is negatively charged and it has that filament. The filament has a high voltage supply, and that high voltage supply does two things. One is it kind of boils off those electrons that we want it to do, and that's called thermionic emission. So the filament has to get really, really hot for that metal to sort of boil off electrons. And then we want it to have a high voltage supply too, that those electrons are really projectiled towards the anode so that they will interact with it. The anode, on the other hand, is positively charged. It's typically made of tungsten or some other heavy metal like that. It has a rotating anode most of the time. The newer ones will have a rotating anode that contains the target material, such as tungsten. And this is where the X-rays are actually produced. So the electrons will come from the cathode, but the X-rays aren't actually produced until those electrons interact with the anode. So as the CT operator, you will select the KVP and the MA settings. A lot of times these are built into the software, the acquisition software of the camera or the scanner. And so you can select the study that you want and it's pre-built into it. However, you do have the ability to change it if needed. So the KVP is the kilovoltage peak. And that one is really the energy of the X-rays. So it's the potential difference between the anode and the cathode, the kinetic energy of the electrons, and it correlates to the maximum X-ray energy. The MA or milliampere setting is the current that's applied to the cathode filament, and this correlates to the number of X-rays that are produced. It has to do with the number of electrons that are released towards the anode and the number of x-rays ultimately. So both of those, if you increase the settings, you will increase the radiation dose. To a certain extent, you can increase the image quality also. So most of the time, technologists don't mess with those settings. Now, if you had a really heavy patient and there was a lot of attenuation, it may benefit to have higher MAs. One thing that newer scanners do is they have a modulation on them that will automatically change the MAS setting and increase it where there's more attenuation or density in the tissue. And that helps to get the best of both worlds, where you're increasing the MAS and optimizing your spatial resolution, but you're not giving the patient any more radiation than absolutely necessary. So the x-rays are produced in the x-ray tube. In CT, the x-ray tube will rotate around the patient, and then it has a set of detectors that are opposite the tube. Those detectors will then measure the x-rays that pass through the patient. X-rays are produced, X-rays that are produced and not detected will provide a measure of attenuation of the object or the patient, and X-rays that are produced but don't interact with the patient will ultimately lead to scatter, and that can degrade the image quality also. X-rays are produced when the electron cloud are accelerated across the X-ray tube to the positively charged anode. This is where they interact with it and create either Bremsstrahlung or characteristic X-ray. Those electrons will strike the focal point of the anode on the target and produce the X-rays. We'll talk about focal point in a second. But of the energy that's applied in the X-ray tube, only 1% are X-rays and 99% of it is heat. So it's very important with X-ray scanners that they are warmed up, first of all, before you start using them. And then also, because you have to give that filament time to warm up and enough to have the voltage that you need to be able to produce the X-rays. But then also it's important to have cooling systems because the entire process does create a lot of heat. So X-ray production depends on 5 factors. First of all, the source of free electrons. You need that filament to be really, really hot for that thermionic emission. The acceleration of electrons, this is, how fast they travel towards the anode. You need a really high, you need a high KVP setting for that to set up that potential difference so that the electrons will pass from the cathode to the anode. Focusing of the electrons, this happens at the cathode, and it's often done using a focusing cup that's either molybdenum or nickel. And this is negatively charged, and it just helps to direct the electrons straight towards the anode. And the deceleration of electrons, this is the bombardment of the target. So this is the stream of electrons that pass through the focusing cup and were directed at the anode. And then when they bombard the target, they'll interact with it. And then you have a total energy transfer. This is the kinetic energy of the accelerated electrons. And it's transferred to that thermal energy and electromagnetic energy. So within the X-ray beam, there are a lot of different X-rays, and there are a lot of different energies mixed in there. We call this polychromatic. Even though the characteristic X-rays are a set amount, there's a lot of different types of characteristic X-rays being produced with different energies. And then you also have the Bremsstrahlung mixed in there. So the low energy X-rays are filtered by passing the X-ray beam through aluminum filters to decrease the patient dose. So these are the really low energy X-rays that will not contribute very much to the image. They'll typically get absorbed by the patient, or they will interact with other things and create scatter. So they have the potential to degrade the image quality, but mostly they increase the patient dose without providing any benefit. So we have that pass through the filter on its way out of the X-ray tube, and that helps to absorb and filter out some of those really low energy X-rays that are not helpful. Next, the beam passes through lead collimators that limit the beam size to the size of the detector array. So this has to do with really the width and depth of the X-ray beam. And then you have those are the pre-collimators. So they define the X-ray beam shape and the width. So that decreases the radiation dose to the patient. It also reduces the scatter because you're able to direct it straight through the patient to the detector arrays rather than just irradiating all the space within that gantry. And then the post collimators, they reduce the amount of scattered photons reaching the detector, and they decrease the noise in the image. Advantages of using thinner collimation or thinner slice thickness: you do have less volume averaging. You also have less streak artifact from really dense objects like bone or metal. And then you also increase your spatial resolution. Some of the disadvantages, though, of using thinner collimation and ultimately thinner slices is an increase in noise. In CT, we sometimes call this quantum model. And then you increase your scan time and you increase the patient dose. The focal point is really the point source of the X-rays, and it will project a single line. A larger source of X-rays produces a penumbra or a blurry line. A focal point has the best resolution, but it would melt the target. So this has to do with when it passes through the focusing cup. So this is when the electrons are leaving the cathode and they're headed towards the anode, and they go through that focusing cup. That helps to set the focal point. If those electrons were in a straight line, then the X-rays would be a straight line, but that would provide good resolution, but it would melt the target. So when they are produced in a cloud or blurry line, and it produces a larger source of X-ray or larger source kind of electron cloud, that produces a larger source of X-rays called a penumbra. The focal spot is going to differ for all the different X-ray producing modalities, but for CT, the ideal focal spot is about 0.75 to 1.5 millimeters. That's going to provide a good compromise and create good spatial resolution. So the detector array is scintillation detectors. They're detecting the X-ray photons that are coming past through the patient. So they are typically solid state detectors, and they are made of silicone, germanium, cadmium, yttrium, gadolinium. There's a lot of different materials that those detectors are made out of, but they are solid state scintillation detectors, just like solid state scintillation detectors in a gamma camera. They're extremely similar to that. There are no photomultiplier tubes in a CT scanner. They use photodiodes instead. And so really you don't need to know the energy of the photons. You just need to know that those X-rays pass through the patient and hit the detector. And so you really just need to count counts, not to analyze those counts. And so photodiodes are great for that. It's just going to tell you when the X-rays hit, and it's going to count them as like a count all that information. We don't really call them counts in CT, but that's essentially what it is. And then the semiconductor junction detects the radiation and generates an electrical signal equivalent. So really all that means is that X-ray passes through the patient, it hits the photodiode, it hit it, and it creates that electronic signal from there. The detectors are aligned in rows, and the number of rows equals the number of slices per scanner. So if you have a 64 slice CT, That's how many rows of detectors there are in the detector array. If you have an 18 slice one, then you have 8 rows of detectors. So um, typically for diagnostic CT, you do want the scanners that are 64 or 128. That gives you a better ability to scan quicker when you're doing things like anything that's like bolus tracking or helical CT or anything like that. It helps to have more rows. But for PET CT, SPEC CT, if you're just doing it for attenuation correction, typically 8 is good enough. If you're doing diagnostic with it, you may want it to have a little bit more rows, like a 16 or 64 slice. But 8 slice is perfectly, or 8 rows of detectors, 8 slice CT is perfect for hybrid imaging. And then the CT data acquisition system, or DOS, basically transmit that information to the computer from the detectors. So this is a CT scanner that's naked. This is a CT scanner with its cover off. And let's see if I can point to it there. This is your detector array, and then your X-ray tube is up here. It's going to be opposite of it because here's the patient table where the patient would lie. And so these always stay opposite of each other, and then they just rotate around the patient. All that other stuff in there is a mix of electronics and mechanics because that does travel at a very high rate of speed. If you ever get a chance to see the CT operating with the cover off, it travels very, very fast. So the CT acquisition, we'll talk about in more detail in another module. But especially for helical CT, there's the slip ring technology that allows it to rotate continuously. Older scanners that did not have the slip ring technology, so this would be generators 1 through 3, I think, or generation 1 through 3 of scanners, something like that. The gantry would make one rotation, and then the electronics and the wiring and everything would get kind of caught up, and it would have to unwind and start over again. That wasn't very beneficial when you're trying to do any kind of bolus tracking or angiography studies or anything like that. And so the slip ring allows it to continuously move in a loop without having to stop and rewind itself and start over. So that's really great for that. The rotation speed is the time that's required for one gantry rotation. So this is the time that it takes for the X-ray to rotate all the way around the patient one time. This is commonly 0.3 to 1 second. The table motion, that correlates to the pitch, how fast the table can move through. And typically it's about 10 to 20 millimeters per second. And then when you're doing a CT acquisition, the very first picture that you take is a scout, depending on the manufacturer. This could be called a scout, a topogram, or a localizer scan. It's all the same thing. It's that initial scan that allows you to select the anatomical regions or parameters for the study. And so with that, the X-ray tube remains stationary and either does like anterior, posterior, or lateral view. And the table will move through the gantry while the X-ray exposes continuously, but the X-ray won't rotate. So you just get like an anterior or posterior view of their anatomy, or you get just a lateral view, depending on which one you took. So CT imaging parameters that the technologist can choose that make a big difference are the KVP and the MAS. Low dose CT tends to be about 80 to 140 kVp. This is what's used for attenuation correction for hybrid imaging, and it may be higher for diagnostic CT. It does depend on the body part being imaged, the size of the patient, and the position of the patient arms, what kind of KVP setting that you use. And if you have a higher KVP, that means you have a higher X-ray energy, which means it's more likely to penetrate through the patient. This will decrease noise. It will decrease beam hardening. It will increase the patient dose, and then eventually it will decrease the contrast because you won't see as much attenuation difference in the tissues. So a higher energy means more of the X-rays pass through the patient and hit the detector. This does reduce the beam hardening, and you don't see a beam hardening artifact as much, but you do decrease the contrast because all the photons are making it through, which is going to make the image appear more black. So if you have a low dose CT and the KVP setting is set really low, your images will look whiter because more of the X-rays are attenuated and less of them are reaching the detector. If you have a high KVP setting, your image is going to be blacker, like the lungs, because more of the X-rays are passing through the patient and hitting the detector. So if it's a low KVP, I always think of it as looking whiter, like the bones, because the bones are really dense and tend to attenuate a lot, and that's why they look white on the image. So I always associate that and think of, yeah, if there's a low KVP setting, then the images will look whiter. And if it's a higher KVP setting, then the images will look blacker like air. The milliamperes per second, the low dose CT, you will decrease the MASs. This will also depend on the patient size, their age, their height, their weight, all that stuff, their body habitus. And the range is typically for low dose CT, 20 to 120 MAS. It could be anywhere from like 200 to 400 or even maybe up to 600, although that would be a really high radiation dose for diagnostic CT. So diagnostic CT, you're going to see it more closer to like 400 MAS or so, 200 to 400, maybe higher if the patient is heavy set. And then for low dose CT that you see in hybrid imaging, it's going to be 20 to 120-ish. The higher MAS setting, the more X-rays you'll produce, which means you have less noise. You also will have better contrast and higher patient dose. So you'll get really good imaging contrast that's low noise, but you will do that by increasing the radiation dose to the patient. Noise in CT is also called quantum model, and this is determined by the number of X-rays. So if you increase your MAS, you're decreasing that noise. And that's a good thing to keep in mind. That's very similar to nuclear medicine. The more counts that you have in the image, the less percentage of noise there is. So that's kind of the same concept, except it's CT. So we can't just take the image for longer because we're acquiring what's coming off the patient. We have to actually produce more counts in the X-ray tube. So other than that, the concept is very similar. And that concludes this CT physics review. I hope you guys enjoyed the video. Thank you.